Hello, everyone. It's my pleasure to come to Quantum Innovation Summit today. I'm Dr. Zhou, Vice President of SpinQ Technology. So what are we going to talk in this keynote? First, we are going to start with a fundamental question. What's a computer? And then let's go through the classical computer, superconducting quantum computer, and the NMR quantum computer. Let's see if they have any similarity between them. So first, let's think about what's a computer. When we talk about computing, the first thing that comes to our mind might be using a phone or a calculator to calculate some complex multiplication, but indeed it's much more than that. Our brain is the earliest tool for computing. No matter whether you are playing chess with your friend, choosing the t-shirt color, or thinking about what's for lunch, you are computing. And we may use some tools to help us with computing. For example, you can use your fingers, you can use the abacus, or use a supercomputer. It doesn't matter what kind of tools you are using. They are just a tool to help us with computing. Later we will see that quantum computer is just another tool for computing, but just even better and faster. So first, let's think about classical computer. 300 years ago, we have the innovation of binary logic. 200 years ago, we have a mechanical computer. 100 years ago, we have electronic computer. It doesn't matter what kind of material you are using. If we can have two states, it can change between the two states, and the state can transfer to some other component. Then we can use it to build our logic. Once the logic gates, once we have the logic gates, building a binary computer is just as simple as building blocks. Here, the Boolean operation are logic operations used to manipulate and calculate truth value. The basic unit of computer operation is the logic gates. Here is the truth value for 3 basic logic gates. And when it comes to the underlying hardware, we are talking about the MOSFET. It works. It works as the switch. For example, here, if that VG at high voltage, then S and D, they are connected. Otherwise, S and D, they are not connected. So what's the relationship between the underlying transistors and the logic gates? Here is an example, the AND gate. In the circuit diagram, we can see if both A and B, they are at high voltage, then the output is connected to 6 volt power supply. Then the output is at high voltage. Otherwise, the output is not connected to the power supply, then the output is at low voltage. Now we have the logic gates, but we need to use the logic gates to solve of the problems that in our lives. Otherwise, they are just beautiful logic gates, but have nothing to do with our life. So here is the half adder. We can use this exclusive OR gate and this computer is better at the couple, the manipulation, and we can is under very low temperature, about 10 millikelvin. This will make sure the aluminum is at superconducting situation, and the qubit won't change to one state because of the heat. And then we use the measurement and control system to measure and control the qubit using radio frequency signal, which is usually between 4 to 8 gigahertz. Here are some real photos. For example, the quantum chip fabrication lab, quantum chip under a microscope, and a whole system, and some signal that we sent out using our arbitrary wave generator. And we have some many material in the freeze, like the circulator, all web-based. You can get access to it through cloud.spinq.cn. Here, indeed, it was animation, but because of time, maybe we can go through it. We have this kind of one-click automatic varying system in the EDA to help you to design your chip quickly. And okay, maybe we can go through this. After you design the chip, the next step is fab your chip in a clean room. Okay, let's go through. Right now, our commercially available quantum chip is the Zhou series. You can have up to 20 qubits, and the single qubit gate fidelity is up to 99.9%. Except the quantum chip, the most important signal, and it controls the qubit state after modulate with the microwave. Similar stuff will happen when we send in the signal through the reading line, and after demodulated, we transport the signal to the quantum analyzer, and then we can get the computation result. And here are some details for the AWG, like it has a radio frequency bandwidth like 450 megahertz, and here is what we can send out, like the SpinQ logo using our AWG. And for the quantum analyzer part, it's 4-channel AWG and a 2-channel collection. And we have some other components. If you have so many qubits to control, you need to use some trigger distributor to make sure all qubits see the signal at the same time. And we have some unique feature to make sure it's best in the speed, accuracy, and convenience. Like if we use distributed edge computing technology with our FPGAs instead of CPU to make sure the speed will be increased significantly. Now we have the chip and the measurement control system. Let's think what can we do with them. First, we can sweep the frequency of the resonator. Like here, we can see 5 cavities. That means we have change to one state, otherwise it's always at 0 state. Then we know the qubit frequency. And then we drive the qubit at this frequency with different pulse lengths. Then we can know what's the pulse length that we need to use to drive our qubit from 0 to 1 state. After that, we can measure some parameters like T1, T2, and the single qubit fidelity. After some complex 2-qubit experiments, we can run our quantum algorithm like the Zhou algorithm or the GSA algorithm in the end. Next part, we are going to have a look at the NMR quantum computer. But for this part, my colleague Dr. Feng will introduce it in detail in the afternoon, so I will have it short. In 2020, we released the world's first programmable quantum desktop quantum computer, Gemini, which can work at room temperature, maintenance-free, and very stable. Now we have this series product mainly for Where is it? Oops. Something wrong. Okay. Something wrong. We have the SpinQ Cup competition every year, and for this part, it's here. if you still remember, we showed you how we do the addition in classical computer. This afternoon, we can also show you how we do the addition on a 3-qubit desktop NMR quantum computer to do this 1 + 1 = 1, 0. Mathematically speaking, this is what's happening behind. And initially, you have 3, 0. After set the initialization, you set Q1, Q2 at 1, 1. And after the half adder, you look at Q3 and Q2, you get 1, 0. This is what's happening in, behind for the half adder on quantum computer. For the time issue, I will go past this part, but I will still would like to share this slide with you. Let's compare the classical computer and the quantum computer. You can see on the classical computer, the bit is the voltage high or low. But for the quantum computer, it's some hardware on the chip. And the logic for classical computer, for example, the NOT gate, is some hardware on the chip. But the logic for quantum computer is the pulse. It's flowing around. And from the mathematical aspect, the basic for classical computer is 0 + 1 = 1, while for quantum computer is some matrix multiplication. And right now for some special tasks, quantum computer is already faster than classical computer. The last slide, let's do an analogy between the vehicle and the computer, because they are so similar in some aspects. For example, if you would like to go to Abu Dhabi from Dubai, you'd better choose a car instead of airplane. If you would like to add 1 and 1, you'd better choose a classical computer. But